Hi everybody, my name is Matt Souter, and for my 405 project, I worked on an aircraft's pitch angle control system. So an aircraft's pitch angle is the angle from the longitudinal direction of the plane and the horizon. All aircrafts have a pitch axis, as shown here in the picture, which is a 90-degree angle to the center of the aircraft. So this axis helps control the longitudinal orientation of an aircraft and is used in planes' autopilot systems to keep the plane steady. Here we have the control system for the aircraft's pitch angle control. To find the system's transfer function, I first need to reduce the system. I started by reducing the loop of the D of A inside the system. After reducing that loop, I can now reduce these three functions within the system to give myself the open loop transfer function. This open loop transfer function will later be used to plot the root locus, but in order to find the transfer function and the time response of the system, I must reduce it further, giving me the transfer function of the system shown here. So in the system we have two variables, K of A and K of R. K of A is the outer loop gain of the system, and K of R is the rate gain. K of A is responsible for the phugoid dampen and oscillation of this system. So we need to assume these two variables for the time response of the system, and I assumed K of A to be 24 and K of R to be 4. I chose these numbers so that I at least have one whole number to work with for the roots with the S plus 4. And without getting too much details into the calculation, and after finding common denominators and equating the sides of the second functions shown here, I was able to find values of A, B, and C, which allowed me to put the function in a format where I can take the inverse Laplace transform and get the time response of the system shown here as G of t. So next I go to plot the root locus using the open loop transfer function that I determined earlier, which is shown here as G2 of S. So for this transfer function, I'm going to use the same K of R value of 4 as we used before. And putting that into the system, we can get a few characteristics of the equation, such as the poles being -10, -5, 0, and that there being no zeros of the system, and that the angles of asymptotes are 60 degrees, 180 degrees, and 300 degrees. Here's a plot of the root locus of the system with a gain of 1. And to start, you'll notice that the zeros of the root locus plot are less than or equal to 0, so the plot is stable. You can see that the system has no overshoot and a low natural frequency since it's not oscillating. This system has a slow response time, about 109 seconds, which isn't ideal for an airplane, which we need a response time hopefully in the milliseconds. But at least for this, we can see how the system works. And just to note, for the gain rate of the open loop transfer function that we used earlier, if we keep increasing that value, it would only increase the rise time of the system, which again wouldn't be ideal for an aircraft system. So changing the K of A and getting a gain of a 150 in the system, we reduce the rise time of 0.366 seconds. We get a settling time of 2.43 seconds and have an overshoot of only 20%. If I continue to increase the gain of the system, I can further reduce that rise time, but it would increase the overshoot and the settling time. And I thought for a response time less than 1 second and a percent overshoot of under 20% would be ideal for this kind of system. This system's response time will allow the plane to quickly adjust the aircraft's pitch angle, whether in autopilot or if taken off landing, in which the pilot needs to properly guide the aircraft. Lastly, I plotted the Bode plot with the gain 150. And with this, we see we have a gain margin of 14 decibels and a phase margin of 48.2 degrees. With that 14 decibels from the magnitude plot, we can calculate K critical of the system of a value of 751. This means the system is stable up until that gain of 751. But as we saw earlier, a higher gain would increase the response time of the system, which would also not be ideal. But overall, that is my project. Thank you all for listening, and have a good day. Thank you.